Hello and welcome. In this introductory lesson, we will learn about two basic concepts of group theory. I expect that you already have some general knowledge about set theory, and you know how to deal with applications and functions. We begin with a very familiar concept, operations. A classical example is the usual operations over numbers, addition, multiplication, subtraction, and division. Operations aren't exclusive for numbers. It's a more abstract notion. For example, we have union and intersection, which are operations that works with sets. Composition is also another example of an operation. It takes two functions and returns a third one. Matrix multiplication is an operation that takes two matrices and return a third one. In all these examples, we see that an operation is a function, an operator, an application, something that takes two things and return a third one of the same class. We formally define binary operations, or operations for short, as functions defined on the Cartesian product of a set and takes values in the set itself. Now I want you to pay attention to the difference between the operations on the left and the ones on the right. We notice that on the left, the order in which we apply the operation doesn't affect the output. On the other hand, swapping elements here changes the result. We call the operations that are independent of order commutative operations. Here is a practice question for you. Are the union and intersection operations commutative? What about functions composition? Pause the video and take your time solving this question before we proceed. The union, and so is the intersection, are order independent, meaning that they are commutative. The composition operation, on the other hand, is not commutative, as we can see in the following counterexample. Another property for operations we care about is associativity, the type of operations that isn't affected by the priority of performing the operation. A good example of this is addition. Subtraction, on the other hand, is not associative. The priority of doing the operation does affect the result. Quick practice question for you. Is function composition associative? Pause the video and give it a shot. The answer is yes, it is associative. As long as you get the order correct, it doesn't matter where you begin composing the functions you have. Until now, we defined the binary operations, and we distinguished two types of them, commutative and associative operations. Now here is a challenge for you. Without using Google or AI, try to think of or define an operation on power sets, like union and intersection, that is not associative. Drop your answer in the comment section so we can discuss it together. After understanding the many types of operations, now we are interested in structures. A structure is a set together with an operation. When we talk about set, we are interested in elements as disconnected, independent objects. But now extend this to look for how these elements interact with each other following the operation we have. The first and most important property is closure. If you take two elements of the set and combine them under the given operation, can you always guarantee that you will stay inside the set? An example for this is the set of reals with multiplication. Any two reals multiplied will result in a real number. What about naturals under subtraction? Well, closure doesn't hold as we can see. Now with the practice question. Is the set of bijective functions closed under composition? Again, I encourage you to pause the video and try it yourself. The answer is yes, since we already know from set theory that composition preserves the bijectivity of functions. After getting that a set is closed under the operation, we are interested in a specific type of elements called identities. An identity is defined simply as the element that preserves other elements unchanged under the given operation. 1, for example, is an identity for multiplication. 0 is an identity for addition. Now, what is the identity of composition? The answer is the identity function, the function that takes an element and returns it unchanged. Now here is a fun challenge for you. Can you find a set and an operation for which there are not one but many identity elements? Give it a shot and drop your answer in the comment section. But remember, it can be an identity from the right or from the left. We are now in a system that is closed under the operation and contains an identity. What we will look for next is the inverse element. When the inverse is combined with its corresponding element, it must return the identity. Elements that have an inverse are called invertible elements. Some example of this is the multiplicative inverse, or negative numbers as additive inverses of the positives. Now I want you to try and identify the inverses of sets when working with the union operation. First, we have to find the identity in this structure. Obviously, you can tell that the identity is the empty set. Now, for a given set H, is there a set S such that the union between them is empty? This can only be true if H itself was the empty set. Thus, the only invertible element is the empty set, and its inverse is the empty set itself. Now we move on to uncover the main concept of this lesson, which is the concept of groups. A group is defined as a structure that satisfies the following criteria. The operation must be associative. The set must be closed under the operation. There should be an identity element in the set, and every element in the set must be invertible. Examples of this are the set of non-zero reals with multiplication, integers with addition, bijective functions with composition. Here is an exercise for us. We consider the set R squared together with the operation defined as following. Is this system a group? First, we check for associativity. And as we can see, the operation is indeed associative. The closure of R squared under the operation is obvious, since R itself is closed under addition and multiplication. Let's now look for an identity. Solving this system gives us 1, 0 as the identity element. What about invertibility? We clearly see that every element is invertible except elements that have 0 as the first token of the pair. So the system does not form a group, since not every element is invertible. Now I want you to tell me, what is the biggest subset of R squared that forms a group under this operation? The answer is the Cartesian product between the non-zero reals and the reals. Associativity holds. The identity is still there. Invertibility also holds. But what about closure? It's easy to check that if the first token of the pair is not 0, then the output will always be non-zero. Thus, the set is indeed closed under the operation, and the system forms a group. Here is another exercise for us. Is the set of bijective polynomials under composition a group? We already checked the associativity of composition. The closure is easy to check. Bijectivity is preserved under composition, and composing a polynomial with another polynomial always produce a polynomial. The identity element for composition is a bijective polynomial itself. What about inverses? We know that every bijective function is invertible. But is the inverse of a polynomial also a polynomial? The answer is no, as you can see in this counterexample. Now take a look at this structure. Does it form a group? Associativity of addition is already known. Closure is also held by combining the integer part and the coefficient of square root of 2. The identity element for addition, which is 0, does exist in the set. And finally, we have that every element in the set is invertible. Thus, the system forms a group. Now, before we finish our video, I want you to think about the properties chosen to define a group. What do you think is the secret behind this particular choice? What do they imply together? And what makes a structure that satisfies all these conditions special and useful? For example, maybe you already noticed that until now, every group we have seen has a single identity element and a single inverse for every element. Why is this true? And how can this be useful later? That's what we will uncover in the next video. How we can use the given information to deduce more and more things about the system we are working on. We will also see how we can extract smaller groups from inside the groups we already have. And by the way, I am curious to know what brings you here. Are you a math student struggling with abstract algebra? Do you study another major maybe that includes the notion of group? Or are you just curious about the subject? Tell me in the comments. And if you find the video helpful, consider hitting the like and subscribe button.